Hey, welcome back to the channel, everybody. This is Kevin. You might remember earlier this year that I got together with a couple of good friends, Charles Judd and Anthony Sequeira, and over the period of 3 days, we taught you topics from the CCNA, the ENCOR, and the ENARSI exams. And I thought for this week's video, it might be fun to show you a segment from the Cert Summit. And in this segment, I'm going to be teaching you 3 topics from the CCNA exam blueprint. Specifically, we'll be covering in this video Network Address Translation, or NAT, Network Time Protocol, NTP, and we'll be talking about the Dynamic Host Configuration Protocol, or DHCP. And this video is longer than normal. I think it's over an hour long, so get comfortable, get some snacks, and do me a favor, if you enjoy this video, please give me a like down below and subscribe so you don't miss any of our weekly content. Now join me from this segment from the Cert Summit. Welcome back, everybody, to our final session. Can you believe it? Session number 6 of 6. It's the part 2 session of day 3 of the Cert Summit. And in this session, we're going to be talking about 3 different IP services that you need to know about on the CCNA exam. And this also kind of bleeds over to the ENCOR exam as well. We're definitely going to be talking about some ENCOR content in this session. Now, we want to start off with Network Address Translation, or NAT. And there's a few different versions of NAT. We're going to be demonstrating several of those different versions. But let's think about what is the purpose in life for NAT? Well, for one thing, we know that we're out of IP version 4 addresses. Well, NAT has allowed us to continue putting up new networks running IP version 4 addressing without overlapping one another's addresses and causing problems. And the way that is, we can have private IP addressing inside of our network. Remember those RFC 1918 addresses that are not routable on the public internet? Well, we could use those inside our organization, and then we could have one or a few publicly routable addresses that our internet service provider gives us or sells us, and we can translate between those private addresses that are not routable on the public internet out to those internet routable addresses. Now let's take a look at how this can work. Here on this topology on screen, and I want to make my camera just a little bit smaller. I know I was overlapping some stuff in the last session, so I'm going to be just a itty-bitty thumbnail up here. Hopefully that will make things a little bit better. There we go. But let's take a look at this topology. We've got a couple of clients on the inside of our network, clients 1 and 2, and we want to get out to this web server that's on the internet. And the way this is going to work is we've got a private IP address of 10.1.1.1 on client 1. It wants to go out to the internet. Well, that's not going to work, is it? That cannot be routable on the public internet. But R1 is a NAT-enabled router. So what's going to happen is the packet comes into R1 and it's destined for 203.113.100, and we're going to translate it. Now, before we get into this, there's some terminology we need to understand. We need to understand the inside versus the outside. That's going to be an important term in a few moments, because when you're configuring NAT, how does the router know? It doesn't know what you consider to be the inside of the network and the outside of the network, so we've got to tell it. There's going to be a command we're going to enter here in a few moments that says this interface is connected to the inside of our network. So in this case, everything to the left of R1 is the inside. Everything to the right of R1 is the outside. And client 1 sends this packet to R1. Notice the source and destination IP addresses. The source is obviously client 1. The destination is that publicly routable IP address of the server. Well, the NAT-enabled router is going to take that private address, that 10.1.1.1, and it's going to convert it into a publicly routable address. And it's going to pick, in this case, from a pool of publicly routable addresses. This particular network, they have the luxury, the uncommon luxury of having more than one publicly routable address. And they'll just pick a publicly routable address from that pool. Perhaps they choose 192.0.2.101. When client 2 wants to go out to the very same server, well, we could give it a different address that can be routed on the public internet. And I want to define some terms for you. Please take some notes on this. This is one of the more confusing parts of NAT, because we've got, if you want to make a little table, we have 4 different kinds of NAT addresses. We have inside local, inside global, outside local, and outside global. Wow, what does all that mean? Well, the first word tells us the device we're talking about. So if I'm talking about client 1 or client 2, it's going to be some kind of inside address, maybe inside local, inside global, but inside says we're talking about a device on the inside of the network. If the first word is outside, then we're talking about a device on the outside of the network, which in this case would be our web server. Okay, what's the difference then between inside local and inside global? Well, let's consider this. Local, you might want to put this in your notes, local is only going to be locally significant. It's not routable in the public internet. It can only be routed locally. Where a global address is globally routable, as the name suggests. So these addresses that are talking about client 1 and client 2, our inside devices that are on the inside of our network, if they have a local address, it's only routable locally, it's in the 10 dot address space, well, those are inside local addresses. What happens is those addresses get translated and go out to the internet. Well, here's where a lot of people get tripped up. They think we're outside the network now. We must be some sort of an outside address. No. What device is it talking about? Yeah, even after R1 translates 10.1.1.1, even after it translates it into 192.0.2.101, it's still talking about a device on the inside of our network. It's still talking about client 1. So it's still an inside address. But now it happens to be a globally routable address. That makes it an inside global address. That is a key point that trips up so many people. Please get that. And then we're talking to the web server. And where does that live? It lives on the outside of our network. Is that a publicly routable address? Yes, it is. So that means the web server's address of 203.0.113.100, that is an outside global address. And our router R1, it's making a NAT routing table, and it's keeping track of this. It knows that 10.1.1.1 gets translated into an inside global address of 192.0.2.101. That way, when the return traffic comes back in, if that return traffic is coming back in and it's got a destination address of 192.0.2.101, the router says, oh, I know who that's for. I'm going to look at my table and see that if the address equals this, then the real inside local address is 10.1.1.1, and it's going to change it, and it's going to send it into the inside network. Now, you might be thinking I left one out. I talked about inside local and inside global and outside global. I didn't talk about an outside local. Is that a thing? Kind of. I doubt that you will ever see one. Here's the idea. Let's say that you've got a couple of corporate sites. You've got site A, site B, and the internet is in between. At each of these sites, you're using a private IP addressing. If you want to go from a private IP address at one site to a private IP address at another site over the public internet, where does that device live? It lives outside of your NAT router, but it's a locally significant address. It can only be routed locally. So that would be an outside local address. That is a pain to set up, I'll tell you. You have to get into a bunch of DNS stuff. You have to have a DNS mapping to translate it into this and that. You don't want to do it that way. There are easier ways to do that. We talked about one yesterday, didn't we? We saw how VXLANs would allow us to route between private IP addresses over a routed network. Or the first thing that comes to mind here, we could just have a tunnel. We could have a GRE tunnel. We could have an IPsec tunnel interconnecting those two sites. It could look local to us. That's a way that we could get to a local address that happens to live at a remote site. But in this case, we had that luxury I mentioned. We had the luxury of a big pool of addresses we could pick from. But we're kind of out of IP version 4 addresses. So what do we normally get from our service provider? I don't know about you, but my service provider, they gave me a whopping one publicly routable IP address for my internet router. But I've got literally dozens of devices inside my home that need to get out to the internet and talk to one another. Well, for those devices, I'm using private address spaces, but they're all sharing that single publicly routable address. How does that work? Because it seems like all the return traffic coming back into my network, it's all going to be going to that one address. once the router gets it, how does it know who to send it to? They're all destined for the same address. The answer is, in addition to keeping track of the source and destination IP addresses, there's a variant of NAT called Port Address Translation, or PAT. It keeps track of port numbers. Remember when we're setting up a session, let's say with a web server, we've got a well-known address of 80 or 443 for HTTP or HTTPS, and we're going to be going to that destination address of 80 or 443. Well, we've also got to have a source address, don't we? That source address is a randomly selected number, sort of in the higher end. Sometimes we call it an ephemeral port number or a dynamic port number. But in this case, take a look at this example. Client 1, it's picking one of those ephemeral port numbers, and it just happened to pick 41,025. And it's going to this web server on the well-known port of 80. Well, when the NAT router gets that, it says, let me make a note of not only the IP address that just came in, I'm going to make a note of the port number. It's ephemeral port number. So when I see return traffic coming back in, I'm going to know where to send it. Now, in this case, I wanted to show you kind of an edge case here. Notice when we're sending it out to the internet, the NATing router has actually changed the source port ID. It changed it to 42,025. That can happen. Let me make this very clear, though. Usually it doesn't. Usually the port number that we had on the inside of the network is just carried on to the outside of the network. But think about this. If I've got a bunch of devices inside of my network, when they're setting up their sessions, like I said, they're just kind of randomly picking one of those ephemeral port numbers. What if they pick the same one? Well, if they pick the same one, the NATing router is going to prevent that overlap. It's going to make sure they're unique. So I'm showing you in this graphic that it doesn't have to be the same as the original ephemeral port number that our client selected, but it usually is. Those overlaps don't happen that often. And when client 2 wants to go out, again, as we go out to this web server, we're all being translated into that one and only one publicly routable IP address we have, which looks like it's 192.0.2.100. But we're keeping track of port number information. And we see that now in the NAT table. So when the return traffic comes back, if it comes back to 192.0.2.100 with a port number of 42,025, we know to send it to client 1. If it comes back in with 42,050, we know to send it to client 2. And another variant of NAT that kind of goes in the opposite direction, but technically you set it up like NAT. It's called port mapping. Now, lots of gamers do this. If you've got some sort of a gaming system and your instructions say you need to open up a certain port so that you can receive incoming connections from the internet, well, those port numbers can be mapped to your gaming console. Let's see, the last time I set this up, the church I was telling you about, they have an accounting server there at the church, and the outside accountants, they come in and they do work on that accounting server, and they use a remote desktop protocol to do that. And I had to set up a mapping to say when traffic is coming in on the remote desktop protocol port, then I'm going to direct it using the same port to this specific inside local address of the accounting computer or the accounting server. So that's a variant of NAT called port mapping that many gamers are very familiar with. Now, let's take a look at how to set this up. And I want to set up both static NAT, where we say, here's a inside local address. I always want it mapped to this inside global address, so it's always going to be the same. Or more commonly, we're going to have a dynamic NAT configuration where we have an access control list that matches all of our inside IP addresses. We don't have to do them one at a time. And this group of addresses matched by this access control list, they're going to go pick an available number, an available IP address out of this pool that we're going to define. And if we don't have a pool, we'll take a look not just at NAT, we'll take a look at PAT, where we can have everybody sharing the same inside global address. So let's go, let me take my picture off the screen. Certainly don't want to block any of the topology or the output. And let's take a look at this basic configuration. We've got a PC at the top, a router R1, and we're going to this internet router at the bottom. And obviously we're going to be setting up NAT, network address translation. We're going to be setting that up on router R1. So let's go over to router R1. And remember earlier I said that the router itself has no clue what we consider to be the inside of the network and what we consider to be the outside of the network. So we need to tell it. Now, if you look at this topology, you can see that gig 0/1, that connects us to the PC. That's inside of our network. So what I'm going to do is I'm going to go into global configuration mode and into interface configuration mode for gig 0/1. And I'm just going to say, hey, you're the inside. And to do that, we use the command IPNAT inside. And by the way, this happens all the time with Viral. Apparently what I just did was incredibly processor intensive, and Viral fusses just a little bit. That I love the terminology they use here. That was a CPU hog. That always happens when I set up NAT, but it's calmed down now, so it's all right. Now I'm going to say what the outside address is. I'll go into interface gigabit 0/2, and I'll say IPNAT outside. Now let's set up this static mapping. And in this case, what is our inside local address? Well, it's the address of the PC. It's 192.168.1.100. And we're going to be mapping it into, and I don't even show you this on screen, but we're saying that we've got an available address that we can map it into of 172.16.1.100. We're assuming that we've got that big pool of addresses. So here's the command. One simple command. I'll say IPNAT inside source static. So in other words, who is my inside address? My inside local address? Well, it's the PC. It's 192.168.1.100. What am I converting that into? I'm converting it into the inside global address of 172.16.1.100. And we're done. Let's see if it works. Let's go over to our PC, and let's see if I can ping the quote-unquote internet. I've got a loopback interface on the internet router, and we'll see if we can ping it. Can I ping 1.1.1.1? Yes, I can. Don't be concerned about that first dot, that first timeout. That was an ARP timeout. The PC said, I have no clue what my next hop's MAC address is, so it sent out an ARP broadcast. Any subsequent pings, they're going to work just fine. Okay, that worked. Let's go take a look at the NAT table that should have been constructed during that. We'll do a show IPNAT translations command. Look at that. The ICMP, by the way, that's our ping. And we see that our inside global, that's what we translated into. That's 172.16.1.100. It translated our inside local address into that. That was the address of the PC. The outside global address, the address we were pinging, was all ones. Now, outside local, this is a little bit misleading. We didn't really have an outside local address in this case, and because we didn't, it just uses the same as the outside global address. So I give 0 meaning to this column in 9 out of 9 cases pretty much. But that shows our translation. But that's not scalable to say this maps to this and this maps to this. If we do have the luxury of having this big pool of addresses, let's do it dynamically where I don't have to do them one at a time. So just staying here live, let's remove our existing configuration. I'm going to bring up my previous configuration and I'm going to negate it by putting a no in front of it. You know what? I'm just going to leave the IPNAT inside and the IPNAT outside commands because they apply to all these configurations that we're going to be doing. You've always got to say who's the inside and who's the outside. Now, let's define who's on the inside of our network. We're going to use an access control list to do that. Remember back on day one, we talked about how an access control list could be used not just to say yes or no, you can be transmitted or you're going to be dropped. We could also use an access control list to match traffic. Well, now we're going to be matching all of the inside traffic. And I'll say access list 1, and all we need, we're just identifying the source And that's what a standard access list can do for us. I'll just use that, and I'll say permit, and I'm going to permit the entire inside network, which is 192.168.1.0, and it's a /24 subnet mask, and we talked earlier about how we create a wildcard mask, and that's going to give us a wildcard mask of 0.0.0.255. So that access list is matching the inside network. Now I need to create a pool of addresses that we can pull from as we're translating these addresses. So I'm going to create a pool, and I'll say IPNAT pool, and I'm going to give it the oh-so-creative name of pool. Well, at least I did it in uppercase. Normally when I'm coming up with something that I'm naming in Cisco iOS, I normally use uppercase. That way when I'm looking through a config, I can say, oh, pool, that's something that I typed in. That's not some sort of an iOS keyword. And I'm going to start the addresses that I have at 172.16.1.100, and let's say that I've got 100 publicly routable IP addresses. Wouldn't that be nice? And I'm going to go through the range of 172.16.1.199. Oh, by the way, yes, I realize that is a private IP address. When I use this, I just stuck with private IP addresses. So squint and pretend this is an outside address, if you would, an outside global or a publicly routable IP address. But I'm just trying to show you how do we do the configuration. So that's my pool. Oh, that's not all. I need to say what the subnet mask is. I'll say net mask 255.255.255.0. And if I could spell, that would be incredibly helpful. Mask. There we go. So to review, we've done two things. Well, we've done three things. Step one, we said, who's the inside, who's the outside? Step two, I created an access control list to identify my inside local addresses. I created a pool to identify my inside global addresses. Now, here comes the connective tissue that ties it all together. I'm going to say IPNAT inside source list 1. So in other words, my inside local addresses are going to be something that matches access control list 1, and we're going to translate those into a member of the pool that was named pool. And we're done. Let's test it again. I'll go to the PC. Can I ping the internet? Yes, I can. Let's go back and look at our NAT table. Let's do another show IP NAT translations. ICMP, yep, that's our ping. And yeah, looks pretty much like it did before, doesn't it? Oh, by the way, there's another command that I kind of like. It's show IPNAT statistics. And this gives you more information about your NAT configuration. For example, if you don't know, if you're maybe on a customer router, you're not sure who they say the inside and outside interfaces are, well, this tells us. We can see how many times we've actually done a translation, how many of those translations have timed out. We can see the pool that we're going to be translating into. We can see the access control list that we're using to identify the inside local addresses. All right, all that to build up to what I think is probably going to be the most common NAT configuration, and that's PAT, Port Address Translation. This is for the very common scenario where our internet service provider gives us a measly single publicly routable IP address, and we've got to get all the devices on the inside of our network to share that IP address. Here's how we do it. First of all, let me get rid of our dynamic NAT configuration. I'll say, go up to our pool command. Oh yeah, let me get rid of this one first. Do I really want to get rid of that? I'll say yes. Let's get rid of the pool I created. And let's get rid of our access list that I created. Okay, I think we're good now. I think we're back to the way we started. Let's now set up port address translation. And actually, I could have left that access control list because we're still going to need an access control list to match all of our inside local addresses. So I'm just going to create it again. It's quick. I'll say access-list. We'll give it a number of 1. And I'm going to permit, not meaning allow, but meaning match, 192.168.1.0, and the wildcard mask is 0.0.0.255. Now check this out. Here's how I say you take all of those inside local addresses and translate them into a single inside global address. Here's how we do it. IPNAT, inside source. The command starts out just like we've been seeing, but this time I'm going to say list 1 is where my inside local addresses are, and I'm going to translate those into whatever IP address happens to be assigned to interface gigabit 0/2. And there's one more thing. If I just left it like this, the first translation would work and the second one would fail because we already used that address that was assigned to interface gigabit 0/2. But if we want to share that among multiple inside local addresses, we've got to give one other keyword, and that other keyword is overload. In fact, if you want to make a note of this, port address translation is commonly called NAT overloading because we're giving this overload keyword. And let's set up a few different connections here. Let's go back over to our PC, and I'm going to connect via HTTP. I've got that enabled on this internet router. I'll say telnet to 1.1.1.1, but on port 80. So that's like opening up a web connection. And it's successful. It says open. We break out of that and disconnect. Let's try just a regular telnet now. And I didn't have it set up to log in, but at least the translation happened. I actually don't know if I've got this set up for secure HTTP or not. Let's try port 443. Does that work? No, it didn't. But let's take a look at our NAT translation. Let's do show IPNAT translations. Look at this. We see those 3 sessions I just set up. The inside local addresses were all the PC, 192.168.1.100, but notice this time we're keeping track of those dynamically chosen ephemeral port numbers. They're all different for our different flows. One was destined for HTTP, one was destined for Telnet, one was destined for HTTPS. That was our outside local address, and that was obviously stored here in our NAT translation table. We were going to an outside global address of 1.1.1.1 on all these different ports, but now when, let's say, the web server, the HTTP server sends return traffic back saying, okay, here's your web page, it's sending it back to 192, or sending it back to, what did we say the inside global was? 172.16.1.1 on port 16386. And our router is going to look at that and it's going to say, oh, that maps to 192.168.1.100 on port 16386. So it knows which flow, it knows which inside device to send it to. That is a much more common implementation of NAT. And that's a look at network address translation. Let's take a quick break right now and see if we have any questions on that. We covered a lot of terminology, a lot of configuration. Let's, if you have questions, remember to pre-pin that with some question marks so I know it's a question for me. And we'll take some quick questions before we go on to our next topic, which is network address, it's network time protocol. Can you please explain identity NAT or NAT exemption to me? I'm having a bit of trouble understanding the use case for it. Identity NAT. Let's see. Do we need NAT and IP version 6? Let's see. RFC 19. Okay. Wow. Lots of questions coming in. What is the maximum number of inside local addresses that can be translated? Wow. Okay. Let's pick a few of these questions to answer. I don't know that there's a maximum number of addresses that we can do this with, as long as we can keep coming up with unique port numbers, and there's tens of thousands of those. That should work fine. When do we use IP NAT outside? We stick that on the outside interface. And we'll take one other question here. Oh, yeah, here's a good one. Do we need to use NAT for IP version 6? Because, after all, we're not running out of IP version 6 addresses anytime soon. So is there a purpose for NAT? Actually, there is. There's actually a NAT version 6. And actually, it's not version 6, it's called NAT 6.4 or NAT 64. What you can use that for is to help merge together a section of your network that's running IP version 4 and a section of your network that's running IP version 6. What it will do is translate an IPv6 address into a corresponding IPv4 address and vice versa. That's primarily where you see NAT used with IP version 6. Great questions. Didn't answer all of them. There were a flood of them coming in, but I tried to pick out some of the really relevant ones. Let's take a look at our next service, which is network time protocol. One of my favorite sayings I've got two favorite quotes about time. The first one is, the reason time exists is so that everything doesn't happen at once. I love that one. But more relevant to our discussion of network time protocol is the saying, a man with one watch always knows what time it is. A man with two watches is never quite sure. Think about that one. Well, we want our network to have one watch, one believable time source. We don't want our different devices to have different clocks. Let's think about how or why that's important and how we can use something called network time protocol in order to assure that. Why does it matter that time be consistent on our network devices? Well, for one reason, if we're doing logging of events and maybe we're doing some troubleshooting and we're sending this information maybe to a syslog server and we're trying to troubleshoot something that happened at 2 a.m. last night. Well, we might see that this device fired off a syslog alert at 1:58. This other one fired something off at 1:59. This other thing happened at 2 o'clock in the morning. Well, because those times were so close together, we might be able to do some what is called event correlation and see if these very different systems that are sending these alerts at roughly the same time, if that can give us a clue as to what was going on. Another reason that it's important to have accurate time is digital certificates. These digital certificates that we use for secure connections, they've got an expiration date and time on them. And if we don't have our clock set and we think it's some other year than it really is, then we might think that a certificate that's valid is really invalid, or vice versa. We might think an invalid certificate is valid. I'll give you another one. I do a lot with IP telephony in the Cisco world, and the time that shows up on your Cisco IP phones, that is learned via NTP, usually from our Cisco Communications Manager server. But it can learn its time via NTP and then it hands it out to the phone. So we want those times to be correct. Those are just a few examples. So how do we all coordinate exact time? Well, Cisco routers do have internal clocks. They're not known for having being like Swiss watch timekeepers. They drift a little bit. They're not great. But if we keep updating them to the correct time, great. They're good. If we can update them ever so often, and that's going to help keep them with the correct time. But who does everybody look to as an authoritative time source? Well, this varies in different countries, but in the United States, it's the Naval Observatory that is the keeper of the official time. They've got a site in Washington, D.C., and they've got another site in Colorado Springs, Colorado. And at these sites, they have atomic clocks. Now, an atomic clock is considered to be the most accurate time source that we can build. Maybe a pulsar is an accurate time source out in the universe, but it's something that we can build is an atomic clock. And the reason we say it's atomic is it uses the element of cesium-133. And cesium-133 has this property where I forget the exact number, but it's a little bit over 9 billion oscillations of cesium-133 of that element. That equals 1 second. I mean, that is very, very accurate. If you're measuring something based on 9+ billion oscillations, we say, okay, that's 1 second. And that's where the true authoritative time comes from. Now, we don't have the ability from our PC in our home to say, well, let me point to one of those clocks and I'll get my time from the best time source there is. No, we don't have that option. But we can point to an internet-based time source. I mean, Google has some. You can just do a web search for NTP time sources. Many of them are publicly available. And I typically use some of the ones from Google when I'm setting up a router. But think about this. You could have your router at your site, the main router maybe going out to the internet, or really any router at your site. It could be the device at your site that's responsible for going out and getting time from one of those internet-based time sources, which get their time maybe from that one of those atomic clocks. We're not going to be able to speak to those atomic clocks directly, but we can get our time from somebody that gets their time from the atomic clock. And now that we've got this device inside of our network that's getting time from the official source, then we can take the time that we have and we can be the time source for our network, and we can spread it out through our network. Now, when I do that, does it seem like we might be using a little bit of accuracy every time we do that? I could see that. I mean, it's like when you used to have, before digital, and people used to try to make copies of VHS tapes or cassettes. You would record one cassette to another, and then you would record that copy and make another copy. Every copy you lost a little bit. Well, I guess technically with time, every time you go from one time source to another, you lose a little fractional bit of accuracy. So there's a measurement of how believable, how authoritative a time source is. And kind of like administrative distance when it comes to writing protocols, we have something called a stratum value. A stratum value. And the lower the value, the more believable a time source. And you can configure your router if you want it to be your time source and not get it from somebody else. I wouldn't recommend that, but maybe in an isolated lab environment you could. You can go in and you can set your time source to a stratum value of 1. That's as low as you can go on a Cisco router, but it actually can go as low as 0. That's what those atomic clocks have. They have a stratum value of 0. And a device on the internet that learns time from one of those stratum 0 clocks, they have a stratum 1 value. You see, every time we make we go one hop, we're incrementing the stratum value. So here we've got the internet clock. We go to router R1. That's a stratum. That R1 has a stratum of 1. And if we go out to our devices and we're the time source for our company, well, we have a stratum value of 2. Every hop there is, we increase the stratum value by 1. And it only goes as high as 15. It's kind of like RIP, the RIP routing protocol. Remember with RIP, if you're 16 hop counts away, you're considered to be unreachable. Well, if your stratum value ever reaches 16, you're considered to be unbelievable. It's like you're too far removed from the original time source to give any reliability to you. So it only goes as high as 15. Now, the NTP protocol, I made a note here on screen that it uses port 123. In fact, it's UDP port 123, not TCP. And here's a memory aid for you in case you might need to know this in a certification environment. This reminds me of the old Jackson 5 song. Do you remember ABC, easy as 1, 2, 3? Well, think of, and I'll try not to sing it, it's hard not to, but think of NTP, easy as 1, 2, 3. Because that's the port number that's being used by NTP. It's UDP port 123. Now let's take a look at how we can set up NTP. Let's go back out to our live interface. I'll take my face off the PC there, just to not get in the way. And let's go to our internet router first of all. We're just using the same topology as we used with NAT. And I want to show you how we can configure this router to be the time source that's not learning from anybody else. Again, this is not a recommendation because unless you're here, I'm in an isolated lab environment, so I need to say somebody's the time source. But normally you would want to learn from somebody on the internet that's eventually learning from one of those atomic clocks. But here's what we could do on a Cisco router. First of all, let's actually set the time. I'll say clock. Actually, I don't even need to be in global configuration mode to do this. I'm going to say clock set. Let's give some context-sensitive help. And it says, okay, what is the current time? Let's do this. Let's pretend that this router on the internet is not in my time zone. let's pretend it's UTC. It's actually at UTC time. It's GMT 0. It's in Greenwich, England, we'll say. So let's see. I'm in Eastern. I'm trying to do the math in my head. I'm 4 hours behind UTC. It's currently 2:30, almost 2:39. So that'd be 6:39 in military time. That would be 18. I did that math really quickly, so I could be totally wrong here. But I'm going to say it's about 18:30. Oh, 18:39. That's the time. But I got to set the date, and the date is April 2nd, 2020. So I've set the date on this internet clock that we're pretending lives over in England somewhere. And now I need to say, what time zone do I live in? Let's go into global configuration mode, and I'll say, my clock is in a time zone that is offset from Universal Time Coordinated, UTC, by 0. I'll say UTC, the offset is 0. I'm actually at UTC. And I'll say here, and again, the command I'm about to give is a command you would not normally give if you're learning time from the internet, which you probably should be. I'm going to say NTP master, and I'm going to give myself a stratum value. Now, I'm not going to have delusions of grandeur and say I have a stratum value of 1. And if I use context-sensitive help, notice we cannot even set ourselves to 0, but I'll set myself to a 3. That'll work. I'll set myself to a stratum value of 3. So our internet router, it is now providing time down to R1, or once we configure R1. To configure R1, let's go into global configuration mode. Oh, let's just verify something first. I'm going to ping one of the IP addresses on that internet router. It's 1.1.1.1. I'm proving to us now that it's reachable, because when I give all the correct commands here in a moment, it's going to look like I messed up. It's going to look like it didn't work. And I'll explain why. And it will work before the glice is over. But right now, just proving it, I don't want you to start troubleshooting before there's a need to. I can get to the internet time source. And let's go into global configuration mode, and I'll say my NTP server is 1.1.1.1. That's the internet. I just proved I could get to it. Now, what's my time zone? Well, my time zone, I'll say clock time zone. Now, I'm in Eastern time, and currently we're in Eastern Daylight Time, but I need to say what it is when we're not doing daylight savings. So I'll say normally, not even normally really, but without doing any adjustments, I'm in Eastern Standard Time, and that's UTC minus 5. However, we do observe daylight savings time where I live, so I'll say in the summertime, we're called EDT for Eastern Daylight Time, and you can go in and say when it changes. I always get that mixed up. I know it's sometime in March and sometime in November where we spring forward and fall back. I don't try to keep up with that. I just use the keyword of recurring. And if you're using Cisco iOS, it's been made in the last 5 years or so, it's going to know exactly when to spring forward and fall back. And at this time, I promise you, I've configured everything correctly. But did it work? Let's do a show clock. It looks to be a few minutes off, doesn't it? And that's just because that's the time it was before I started doing anything. It looks like NTP isn't doing a great job. So let's do a show NTP status. This does not look good. It says the clock is unsynchronized. The stratum value is 16, which we said was unbelievable. And look at this. Even though I just configured it a second ago, it says I have no reference clock. What's up with that? Well, oddly enough, this is normal behavior for NTP. Specifically, Cisco iOS routers, they're running NTP version 4, and they don't jump to conclusions, I guess we should say. They're going to, in fact, I could do a debug NTP events, and occasionally we'll see, let's do, yeah, that'll work. Debug NTP events. Now, every minute or so, we'll see that there is an exchange. There's periodic communication between my router and the internet router. But it's going to make sure over a period of time that the clock is not drifting. It's also trying to measure how much offset there is between ourselves and that clock. And it's going to take, no kidding, about 15 minutes to actually synchronize. And in that time, we will probably have moved on to the DHCP configuration. And if I forget it, let me just do a debug. Let's do a debug NTP. Packet. Maybe we'll get something there. If I forget, somebody please remind me that in about 15 minutes or so, in fact, I'm going to set a timer. Set timer for 15 minutes.
Okay, 15 minutes and counting.
Okay, that will remind me to come back and see if we have synchronized. But as of right now, and I'm not going to stick around long enough to see the debug packets pop up, so I'll just do a UAll. But right now, if I say show NTP status, it looks not good. We're unsynchronized. Our stratum is 16. I have no reference clock. All right, we're not going to touch that right now, but we're going to come back and yeah, I wanted to show you one other thing with NTP that I wanted to be synchronized first. I wanted to show you NTP security, which is something you might want to know if you're taking the ENCOR exam. So I'll tell you what, when we come back and verify that the time is correct, then I'll show you how to set up NTP security. For now, though, let's move on to our next service. And our next service is going to be DHCP. Now, we're not leaving NTP. We're coming back. We just got to give it 15 minutes. We're coming back to that, and I want to show you how to secure it. But in the meantime, let's talk about our other service, which is DHCP, the Dynamic Host Configuration Protocol. We love DHCP because can you imagine having to go around and statically configure IP addresses on all of your devices? That's administratively intense. Fortunately, DHCP comes to the rescue by allowing us to set up a server that will hand out IP addresses to our devices. And it's going to work much like this. It's going to go through a 4-step process I'd love for you to put in your notes. I don't know about you, but when I guess I'm showing my age again, when my daughters were really young, they used to watch the Nickelodeon show Dora the Explorer. Anybody watched? In fact, recently, there's a movie out, Dora and the Lost City of Gold or something like that. I've not seen it. It looks like it'll be funny, but there's a live action Dora movie now. But I always think of Dora the Explorer when I'm thinking about DHCP because the acronym of DORA explains the 4-step process of the Dynamic Host Configuration Protocol. Let's say, for example, that laptop A just boots up. And it needs to get some IP address information, so it's going to send a broadcast out on the network because it doesn't know where a DHCP server lives. It's going to send a broadcast out on the network to say, hey, are there any DHCP servers out there? And we've got one, and it's going to respond to that broadcast. So watch this with me. Remember, it's a broadcast, so when it gets to the switch, what's the switch going to do? What does it do with the broadcast? It floods the broadcast out of all ports other than the port the packet was received on, which means the switch is going to send it to the server and the switch is going to send it to the router. Does a broadcast cross a router? It does not. So you'll notice it doesn't make it through the router, but it will get to the DHCP server. And that first message is the D in Dora. It's the discover message. We're trying to discover a DHCP server by kind of broadcasting out, are there any DHCP servers out there? And in this case, there is one. And it's going to respond with the O in Dora. It's going to respond with an offer saying, yes, I'm a DHCP server. I would like to offer my services. And here's my IP address. Awesome. Now the laptop knows a destination IP address where it can say, okay, can you please give me some IP address information? So we're going to send a packet directly to the DHCP server. It's no longer a broadcast. That's the R in Dora. That's the request. Now, you might be wondering, how is that packet possible? Yeah, we now know the destination address, but the laptop, that's the whole point of this. The laptop doesn't have an address. What was the source IP address in that packet? It was all zeros. It was 0.0.0.0. That's what it temporarily uses as its source IP address as it's going out and requesting its actual IP address information. So far we've got discover, Is there a DHCP server out there? One responds with an offer saying, yes, and here's my IP address. Then we send a request saying, okay, give me some IP address information. And finally, the ANDORA, the acknowledgement, that's where we do the big download. That's where the DHCP server says, all right, here you go. Here is your IP address information. And that's the ANDORA, that's the acknowledgement. And that's the way that laptop A got its address. It has an address now of 192.168.1.100. However, take a look at laptop B down at the bottom. It has a router separating it from the DHCP server. What's going to happen when we send out that Discover broadcast? A broadcast does not cross a router. What happens? That Discover broadcast, poof, it gets dropped. Do we have to go install a DHCP server on our subnet? No, what we can do is make that router into a DHCP relay agent, or some people call it an IP helper configuration, because that's the command that we're going to be using. If we configure this with the IP helper command, as I'm going to do for you live here in just a few moments, we're telling the router to make an exception for specific types of broadcasts. We're going to say, in fact, there are 9 types of broadcasts that it applies to. There's boot P, there's DHCP, and I don't remember what the other 7 are. But DHCP is one of them. And it's going to say, if you receive a DHCP broadcast, then forward it to this destination. And we can specify the DHCP server as that destination. We can say, go to 192.168.1.2. Or we could just say, go to this network. We can give a directed broadcast address to go to everybody throughout another subnet, and maybe we have 1 or 2 DHCP servers on that subnet. But here, I'm just going to set it up in our example where we point to the IP address of the server. Once we've got that configured, then the packet makes it through, the offer comes back, and the whole DORA process continues on once we have each other's IP address. But the way we got that initial Discover broadcast through that pesky router is that we configured it as a DHCP relay agent, and now at long last, laptop B has its IP address. That's the way it works. But let's dig a little bit deeper. Let's talk about some of the different options for DHCP, some of the different things that we can set up, because it's got a lot of options. For example, we can, if we always want the same device to always have the same address, we can set up a mapping. We can set up some MAC address reservations where this MAC address always is going to be mapped to a specific IP address. So for example, I'm giving you an example on screen of that one MAC address can always be mapped to 192.168.1.125. And we can set up multiple pools of addresses, maybe a different pool for different subnets. By the way, if you work with Microsoft Windows Server, if you work with their DHCP server, they typically use the term scope to refer to this pool of IP addresses. So we can use those terms interchangeably, a pool or scope. Notice I've got a couple of pools here. I've got a pool of 192.168.1.100, and that 4th octet can go from 100 all the way through 199. And you see I've got another pool of addresses as well. We can set up different pools for different subnets. And you might wonder, when this Discover broadcast comes in, how do we know which pool to give it an IP address from? Well, we can know the interface that was the ingress interface. We know what its network was, and we know it needs to be part of that network. And if we want to, we can exclude some IP addresses. Maybe there are some IP addresses we don't want to hand out. We've got some statically configured IP addresses, maybe like the router interface as an example. Maybe we've got servers. Maybe we've got printers that we're pointing to by their IP address. We don't want those to be handed out to somebody else. So we can say, don't hand out the specific IP addresses. For example, we can set up a range. Notice in the example on the right-hand side of the screen, I say, I want to exclude 192.168.1.1 all the way through 99. Then I can start at 100, but I want to stop right after 200. So I want to stop after 199. So I'll follow that up with another exclusion command that says exclude 192.168.1.200 through 254. What's left? What's in between? What's left in between is that 100 through 199. So we've allocated 100 addresses that we can hand out as part of that pool. And when we're handing out IP addresses, it's not just here's an IP address in your subnet mask. There's a lot of information that a DHCP server can give us. For example, it's going to give us our default gateway. It's probably going to give us our DNS server. It can even give us a time to live value for our packets. And in the reason I included another option, 150, that's the address of a TFTP server. We use that a lot in the IP telephony world, because when a Cisco IP phone boots up, it doesn't have a configuration. It needs to go download its configuration file from a TFTP server. How does it know where that TFTP server lives? Well, when it sends out its DHCP request, the DHCP server sends it back. Here's your IP address and subnet mask and default gateway and option 150, which is the IP address of a TFTP server. The phone then goes out and downloads from that TFTP server its configuration file. Oh, remember yesterday, Charles was telling us about Cisco DNA Center. And he was talking about the different things that Cisco DNA Center could do for us, like provisioning. What we can do with Cisco DNA Center is if I'm going to be sending a router out to some remote site somewhere, and the network administrator there is not a CCIE, we'll say, we don't want them to have to do the configuration. We can set everything up ahead of time. We can provision it. We can configure it before it's even shipped out to the destination. And then when they plug it in, when they plug in their device and plug it into the network, it will go out to a server, a DHCP server, which is going to give it the address of a DNS server and maybe a TFTP server, and it can go out and it can download its configuration from a server as well. So DHCP can be used for a lot more than just handing out a single IP address and default gateway. And those are a few of the options you see here. Now, let's talk about lease timers. A lot of people will assume that, okay, I got a DHCP address assigned to me. It's good until I turn my machine off. No, a DHCP address that you're given is actually a lease. It's like when you're leasing an apartment. You get it for a certain period of time. Now, most people, when they lease an apartment, they're not going to wait till their lease runs out and run over to the office and say, all right, I'd like to renew my lease. It's expired. No, they want to renew ahead of time. They don't want to be out on the street. They don't want to have any interruption in service. So what they will do is they'll, well in advance of their lease expiration, they'll go to the management and say, hey, I'd like to renew my lease for another year or whatever. Well, that's what DHCP does. After, let's say that we've got a lease period of, let's make it easy math. Let's say it's 8 days. You're given this, and you can set that on your server. You can say what the lease period is. But let's say that we've been given a lease period of 8 days. Well, at one half of that time, after 4 days, we're going to go back to that DHCP server and say, hey, can you renew my lease? I'll keep the same IP address, but can you just renew me for another 8 days? And it'll say, hopefully, if it's there, if it's available, it'll say, sure. And you're renewed for another 8 days. But if that doesn't happen, maybe that DHCP server is having issues, it's down for maintenance, it's not reachable for whatever reason, well, at least we've still got an IP address for 4 more days, so we're going to wait a little longer. We'll wait until we hit 7 days. In other words, 7/8 of the lease period. At 7/8 of the lease period, which is 7 days in our case, we're going to try again to renew our lease. And hopefully then the DHCP server is going to be active. So we're not going to wait to the end to try to renew our lease. And finally, notice I put on screen that we've got something called DHCP version 6. You can have DHCP version 6 servers for IP version 6 networks, but they can be used in a couple of different ways. Let's think about how an IP version 4 client gets its IP address information. Well, it goes out to the DHCP server, and the server says, here's your IP address, here's your subnet mask, here's your default gateway, maybe some extra information like here's your DNS server. It all comes from the DHCP server. Now, with DHCP version 6, we can still do that. We can have an IP version 6 client get all of its information from the DHCP server. If we're doing that, that's called stateful DHCP version 6. Stateful means we're getting everything from that server. But IP6 has some bells and whistles that we don't, IP version 6 has some bells and whistles that we do not have with IP version 4. For example, with IP version 6, we can learn what network we're on and how long the prefix length is. It's called the prefix length is actually what it's called. The prefix is like the network address, and here the length is how many bits it is. We can go out to the router and say, what's my prefix length? Or in other words, what network am I on? Oh, our 15 minutes are up. So as soon as I finish this, well, let me finish my DHCP discussion, then we'll jump back. But just real quick, let's see. Is it working now? I said we'd check after 15 minutes. Am I on the wrong router? Oh, I'm sorry. I need to do NTP. Show NTP status. That's what I meant to do. Oh, look at this. We've got a stratum of 4. It knows our reference clock. It says it's unsynchronized. More on that later, but at least if I do a show clock, yeah, it's now synchronized. It is now accurate. So we'll come back later and I'll talk about why it says unsynchronized. I don't want to get away from our DHCP discussion, but I did want to prove to you after 15 minutes that it worked, and it did. And notice it had a stratum value of 4, and that's because it learned time from the router that we set up that had a stratum value of 3, so it got incremented 1. But back to our DHCP discussion. If we're doing stateful DHCP version 6, we get all the information. But I could use something called a neighbor solicitation or router solicitation from an IP version 6 client to go out and request information from my router to say, what is my prefix and length? Basically, what network am I on? How many bits are making up the network? And it might say, well, you've got a 64-bit network, and here it is. And we've got a 128-bit IP version 6 address. So we know the network, but we don't know our address on the network. We don't know the host portion of that address, those extra 64 bits. Well, that client can generate that on its own using something called EUI64. EUI64 takes the 48-bit MAC address that's burned into the network interface card, it splits it in half, it inserts 4 hexadecimal digits, it flips the 7th bit. I'm not trying to get you to remember this, I'm just showing you that there are some manipulations that go on, and we end up with a 64-bit address that we can use for the host, and we just kind of stick those guys together, and we've got our address. We don't need to know our IP address from our DHCP server. We learned all that by self-generating and getting the network information from the router. We could still use the DHCP server to give us supplementary information, though, like a DNS server or like a TFTP server. It could still tell us that. But if we're using that DHCP version 6 server for just partial information, in that case, it's called stateless DHCP version 6. So stateful DHCP version 6 gives us everything from the server. Stateless gives us maybe some things from the server and other things we generate locally. All right, that's the theory of DHCP. Let's take a look at a demo, and then we'll go back and we'll talk NTP for a moment. But let's take a look at this DHCP demo, and I'm going to go back out to our live interface. I've got a slightly different topology that we're going to use here. I've got some different routers that we're using. Excuse me. But here in this topology, we've got a DHCP server down at the bottom, and we've got router R1, and we've got our PC. Now, let's go to the PC. In fact, we're at the PC right now. Let me show you how we can tell. By the way, yes, this PC is not a PC. It's a Cisco router acting as a PC. I'm not running a routing protocol on it. For example, I just have we can just statically set a default gateway, but it's not acting really as a router. It's going to learn all that information via DHCP. I just wanted to show you how you can tell a router interface to learn its IP address via DHCP. Because this is what you would do if you were pointing out to your internet service provider. Here it is. Instead of saying IP address and then giving an address, I have gigabit Ethernet 0/1 pointing out to router R1, and I said IP address DHCP. Let's see if we have an address. Let's do a show IP interface brief command for interface Ethernet or gigabit Ethernet 0/1, and it says it's unassigned. Now the method is DHCP. We know that we're supposed to be getting it via DHCP, but currently it's unassigned. I mean, everything's up at layer 1 and layer 2, but we don't have an address yet. Well, no wonder. We've not yet configured a DHCP server. Let's go do that over on our DHCP server. I want to show you how to make a Cisco router into a DHCP server. Let's go into global configuration mode. And remember we talked about excluding addresses? As kind of a best practice, I like to exclude addresses before I set up the pools. My fear is somebody's going to come online and they're going to request an IP address and I'm going to give them one. And it might be one of those that I'm about to exclude, but I haven't excluded them yet. So I always like to do my exclusions first. I'm going to say IP DHCP excluded -address, and I'm going to give a range. I want to exclude the addresses in the range of 192.168.1.1 all the way through 192.168.1.99. So I'm going to start at 192.168.1.100. That's going to be the first address I can hand out. And I want to stop after I get to 199. So I'm going to say exclude 192.168.1.200 all the way through 192.168.1.254. Everything in between, those are valid addresses to hand out. I can hand out 192.168.1.100 all the way through 199. Now let's create a pool of addresses to hand out to the PC. I'll say IP DHCP pool, and I'm going to give it a name of PC. Here, I'm going to say what network. In other words, what's the network from which I'm going to be throwing out addresses to these clients? I'll say the network is 192.168.1.0 with a 24-bit subnet mask. So that's the network. We're going to be handing out an address from that address space, avoiding the excluded addresses, of course. And I need to say what its next top gateway is, its default router, which is going to be R1. And I'll say that the default router is 192.168.1.1. Awesome. And I don't have a DNS server in this topology, but just for fun, let's pretend, and I'll say DNS-server, and let's pretend it's 172.16.1.2. So that's the information I'm going to be handing out to this PC. Let's do a copy run star. Let's go back to the PC. Do you think I have an IP address at this point? Let's try. Let's do show IP interface brief again. I still don't have an IP address. Can anybody help me out with that? In the chat, can you chat into me and tell me what you think is wrong? Did I misconfigure something, or is something else going on? Why has this PC not been able to obtain an IP address? I'm pretty sure that I configured the DHCP server correctly. Oh, somebody says I need to bounce the interface. I think that's a great idea, because that will shake things up a lot. It'll make me it'll make it go out and request again. So let's go into interface gigabit 0/1. Yeah, I actually do that quite a bit. And I'll do a bounce. I'll do a shutdown, a shut, and a no shut. And let's do a show IP interface brief. Still no joy. Anybody else? Big Eric is saying, I need relay to get to the other network. Yeah, notice we've got router R1 sitting smack dab in the middle of our topology. When that D and DORA goes out, the discover, it's going to say, nope, this is a broadcast. I'm not going to forward that. And our discover broadcast is being dropped by R1. It never has an opportunity to get to our DHCP server. Let's fix that. Let's go back over to R1. And let's go into interface gigabit 0/1. That's the interface that's going to be receiving the broadcast. We need to be careful and do this on the right interface. And I'm going to configure an IP helper address. I'll say IP helper-address, and I'm going to specify the address of my DHCP server. I'm going to say 172.16.1.2. In other words, when I receive one of 9 different kinds of broadcasts, including a Discover broadcast, when I receive one of those broadcasts, I'm going to forward it as a unicast to 172.16.1.2. Let's go back to the PC. Let's see if things are better now. Still not yet, but let's use that earlier recommendation of bouncing the interface. I'm going to do a shutdown. Oh, need to go into interface gigabit 0/1. Let's do a shutdown. Oh, I was too impatient. Look at that. It got an IP address right before I shut it down. Great. Now I'm going to have to do it again. I'll do a no shutdown. But you see right here, it said it was assigned an IP address. Hopefully we'll get another one or the same one back. Let's do a show IP interface brief. Yeah, we got one now. Look at that. We've been assigned 192.168.1.101 via DHCP. So that is a way, or that is a look at how we can configure a Cisco router as a DHCP server. We saw how to make a router act as a DHCP client and request IP address information, and we saw how we could set up a router sitting in the middle to act as a DHCP relay agent. Now, while we're still out in the live interface, let's hop real quick back over to our router where we were trying to get time. And if I do a show NTP status, remember things were a lot better earlier. We said we had a strata value of 4. We do have a reference clock, and in fact, I did a show clock, and it was correct. But notice it says clock is unsynchronized. Is that a problem? Did we do something wrong? Actually, no. The reason that it's doing that is because we're running this in Cisco Viral. We're running it in an emulator. And in this emulator, this root dispersion value gets to, I forget exactly what the threshold is. I think it might be 100 milliseconds, but it gets too big. The root dispersion value gets too large. In other words, the time that we calculate between us and our neighbor is a little too much for us to think it's really synchronized. So if we exceed that threshold, it says it's unsynchronized. But we set things up correctly. So I want to set your mind at ease. It's because this root dispersion value is too high because we're running Cisco Viral. But everything was configured correctly. Hey, I hope you enjoyed that replay from the Cert Summit. And if you'd like to get the entire Cert Summit replay, I want to offer you a 30% discount. Just click on the link below and you'll be taken to the order page to get a 30% discount on the Cert Summit and see all the different topics that we cover. Thanks a lot for joining us. We'll see you next time.